Dear students, from this class onwards, you will be learning FIR filter designing. The filters designed by the filters designed by using finite samples of impulse response are called FIR filters. Various steps in designing FIR filter. The very first step is to choose an ideal, that is desired frequency response of digital filter HD of e raised to j omega. Choose an ideal or desired frequency response HD of e raised to j omega. In second step, we have to take inverse Fourier transform of HD of e raised to j omega to find out HD of n, or capital H of k, that is discrete Fourier transform of finite impulse response H of n. Take inverse Fourier transform of HD of e raised to j omega to get HD of n or capital H of k. After finding HD of n, which is an infinite duration sequence, convert HD of n into a finite duration sequence H of n. Which is an infinite duration sequence into a finite duration sequence h of n. If hd of n is determined, then convert hd of n, which is an infinite duration sequence, into a finite duration sequence h of n. Or if h of k is determined, then take n point inverse dft to get h of n. Which means whether I find hd of n or h of k, in second step I have to get h of n either from hd of n or from h of k. Take z transform of h of n obtained in step 3 to get h of z, where h of z is the transfer function of digital filter. Choose a suitable structure and realize the digital filter. Lastly, verify the design. In order to verify the design, determine the actual frequency response h of e raised to j omega of the filter by letting z equal to e raised to j omega, because now we are having h of z at our hand. Therefore, in place of z we have to substitute for e raised to j omega in h of z and sketch the magnitude response of h of e raised to j omega. Dear students, you will understand more about these various steps in designing a FIR filter as and how we proceed. So here you will have to have a little bit of patience. Now we will see how an LTI system can be used as a frequency selective filter. LTI system as frequency selective filter. Let us consider a discrete time signal x of n with frequency content in a band of frequencies omega between omega 1 and omega 2. Let x of e raised to j omega be Fourier transform of x of n, which means that if we take Fourier transform of x of n, that is discrete time signal, that will be transformed into a frequency domain signal x of e raised to j omega. Now x of e raised to j omega will be band limited signal, that is x of e raised to j omega is equal to 0 for omega greater than or equal to omega 1 and omega less than or equal to omega 2, and is equal to 0 for omega less than omega 1 and omega greater than omega 2. Let this signal be passed through an LTI system with frequency response h of e raised to j omega equal to c into e raised to minus j alpha omega for omega greater than or equal to omega 1 and less than or equal to omega 2 and equal to 0 for omega greater than for omega 1 greater than omega and omega greater than omega 2. Where C and alpha are positive constants. Let h of n be impulse response of the LTI system which is obtained by inverse Fourier transform. See, in this subject we are making use of Fourier transform, inverse Fourier transform, discrete Fourier transform, circular convolution, linear convolution. Therefore, to understand this digital signal processing subject, it is very much essential to understand signals and systems subject. That is why we have mentioned in this subject syllabus copy that signals and systems is prerequisite for this DSP subject. Of h of e raised to j omega. Now, the response y of n of LTI system is given by I hope you all remember this basic LTI system input, output and impulse response diagram. The impulse response of the LTI system is h of n, input is x of n and output is y of n. Y of n is obtained by convolving x of n with h of n. That is, y of n is equal to x of n convolved with h of n. If we take Fourier transform of this equation here, that is output equation, we get, on taking Fourier transform of y of n y of e raised to j omega equal to x of e raised to j omega into h of e raised to j omega. But h of e raised to j omega is c into e raised to minus j alpha omega. In frequency domain, I am writing y of e raised to j omega equal to x of e raised to j omega into h of e raised to j omega, because convolution sum in time domain becomes multiplication in frequency domain. Now this may be written as c into x of e raised to j omega into e raised to minus j alpha omega. On taking inverse Fourier transform of above equation we get y of n equal to c into x of n minus alpha. Here we are making use of shifting property of Fourier transform. From the above equation, for y of n, we can say that it is simply a delayed and amplitude scaled version of the input signal. A pure delay is tolerable and is not considered as distortion of the signal. Likewise, amplitude scaling also. Hence, the LTS system defined by band limited frequency response h of e raised to j omega represents an ideal filter. The frequency response h of e raised to j omega is a complex quantity. Hence, we can write h of e raised to j omega equal to magnitude of h of e raised to j omega at angle of h of e raised to j omega, that is equal to c into e raised to minus j alpha omega, where magnitude of h of e raised to j omega is equal to c and angle of h of e raised to j omega is equal to minus alpha omega, because here e raised to minus j alpha omega is of the form e raised to minus j theta. So c is magnitude and minus alpha omega is phase. Since magnitude of frequency response is constant, and its phase is a linear function of frequency an LTI system considered here represents linear phase filter. Dear students, I will stop the class here and continue in next class with ideal frequency response of linear phase FIR filters. I will stop the class here. Thank you.